Swayam Prabha. Digital India. Educated India.
Hello everyone. In the last few set of lectures, we have seen that how a collection of objects we can define using sets. And also we have seen that how to associate a relation between two elements in a set. In today's lecture and in subsequent lectures, we are trying to see how to relate a particular set of elements towards other sets. And we will see what we call as the functionality, or in short the functions of an algebraic structure, and we will try to define certain properties and try to derive certain theorems of these set of functions. Functions are defined as a relation from set of elements A to set of elements B. The only restriction in this relation is that the ordered pairs that are present in the relation can have one element of A occurring exactly once in the first component of the ordered pair, which means that an element of A cannot be associated or related with two different elements of B. Formally, we write such kind of a mapping or function as f of A is equal to B, where we say that the element A is related to element B in the ordered pair, and this relation associating each A to an unique B is the trademark of selecting it or of calling it as a function. Therefore, we can say that AB and AC, if both are present in part of the relation which we name as function, this could not happen unless B is equal to C. So, for each A, I could have a unique association with an element in B. That is the only restriction over the set of relation function defines. Two sets A and B is non-empty, and we define a function from A to B when this condition is satisfied. An example of a function you have already used array or two-dimensional array in your programming assignments. So two-dimensional array, basically you visualize that logical visualization of array from your part is of m rows and n columns. However, it is not the case that in memory this is stored as you visualize it in terms of two dimensions. In memory, since it's a one-dimensional memory, therefore in memory you see such thing stored in row measure fashion, which means that you first store n elements or n column elements in a row, followed by in the next set of n elements from the second row, followed by the next set of n elements in the third row. So in this way, you try to store all the elements of a two-dimensional array. However, to access an element from a two-dimensional array, we use a function which is called I minus 1 into n plus j to access the ijth element. Why? Because let's say I am accessing second row, third column, which means that I have to leave aside all the first n elements, which is from the first row, then go to third element. So second row means 2 minus 1 into n, which is n plus 3. So I leave n elements and then go to the third element to access. So this is a function of accessing array elements from memory location. Mathematical functions you have used, let's say we define a function from set R associating to set Z. We define two functions, one is floor of x, one is ceiling of x. In programming you have used this function. Floor of x means the greatest integer that is just less than x. Ceil of y means the lowest integer that is more than y. So if you now see that 2.7, if you take fx, that is the floor of 2.7, it is the greatest integer that is less than this is 2. Minus 2.7, the greatest integer that is less than this is minus 3. However, if you give integers, it remains as it is, because it is the greatest integer that is less than equal to that. In ceiling functions, we do just the dual. So it's the least integer that is greater than equal to 2.7 minus 2.7 and so on. So these two are functions from real, taking a real as and associating with an integer. We define image and pre-image of a function as follows, that let A is from set A and B is from set B. We say f A equal to B, that is we associate A to B, and we call B as the image of A and A as the pre-image of B. In the function from a set, associating a set to another set B, we say that the first set, which is A, is my domain and the second set is my codomain. The range is all images that for all elements in A you associate it with B. So therefore you get a set of elements in B. That set of elements could be B whole itself, or could be a subset, because the elements that get associated with B, if you take only those, so it forms the set FA, which is for all A's you are getting a set of elements in B which is a subset of B. So we call FA as the range, the set of all images for the elements in A. Pictorially, we see that this is a domain and this is a codomain. We define a function from this domain mapping to this domain, where each element, let's say A, gets mapped to an element B here. So we call B as an image, A as a pre-image, F as a function mapping from A to B. The whole set of elements in A gets mapped into these subset of elements in B. Therefore, we call this subset of element as the range of A. So this is the definition as for functions and its associated notions. Immediate question comes is that how many functions are possible in total? It is not relation. It is a little bit of restriction than what we allow in relation. So let us try to count it. Suppose A is of m elements, B is of n elements. So we are trying to map each element of A here to B. So therefore our definition says that if A1 is present in an ordered pair and it's mapped to someone in B, the A1 cannot again occur in another order paired first component and map to some other element or map. So for a particular element it could map to one element in B. So that is the definition of function. So here we have n such pairs possible for every A to be mapped with B. Now x1 can take b1 up to bn this n values. x2 also can take b1 up to bn this n values. Why? Because it could be the case that a1 is mapped to b1, a2 is also mapped to b2. Consider the function x square, where minus 2 whole square is 4 and plus 2 whole square is 4. So a1 and a2, minus 2 and plus 2 are different, but it maps to the same value. So therefore this particular tuple has choice to take n number of b's in this position. This particular pair has the choice to take from this n elements anything. So going by the product rule in this m positions, we have the total count as n into n up to m times. So it is n to the power m is the total number of functions that we can have from set A to B of size m and n respectively. So it is the cardinality of B to the power the cardinality of A. We define image of a subset. As you can know, the image of a whole set is FA, which is a subset of B. Now if we choose a subset of element from this set A, that is A dash is a subset of A, then the image that A dash produce, we call it as an image of a subset. So these are all the B's that get produced by the relation FA, because it follows the same relation, only I have restricted my domain and make it a subset of that domain. So we call FA as the image of A dash under F. So this is the image of a subset. We can restrict a function by not allowing it for the whole domain to get associated. Again, we can allow only a subset of the domain. So we restrict the function with respect to that subset of the domain as A dash to B and call it as restriction, where each of these element in A dash follows the same rule or association as the function f declares. So it's just we are reducing the number of elements to be mapped into a subset of elements. So we call this function as a restriction of function f to a dash. Similar vein, we can also define extension. Extension is that suppose we have declared a set of functions to be mapped or associated to B, then we can also declare some set of additional elements including those as well, where for those elements which are in A dash, so your additional set is A, which is a superset of A dash. So your A contains all the elements in A dash plus some more elements. So for all the elements in A dash, it will follow the same rule as the function dictates. For the other elements, I do not specify anything here. So therefore, you extend this set of domain mapping to a greater element domain. That's why we call the function g to be an extension of f to A. This is restriction of f to A dash, and this is extension of this function to A. That is how the definition goes. With this definition, we have the first few theorems that let f is a function from A to B where there are two subsets. This is not belongs to, this will be a subset equal to. This sign is wrong. Please note it, this sign is wrong. This is subset equal to A. So these two are subsets of A. Then we have, if A1 is a subset of A2, it implies if A1 is a subset of A2. If A1 union A2 should be equal to if A1 union FA2, and if A1 intersection A2 is a subset of if A1 intersection FA2. So this, remember, this is a subset. So I am just proving you the third one, this one. Okay, so this will be 3. The third one I am proving it because the rest are similar. See, what we need to show here, we need to show that an element that belongs to this if A1 union intersection A2 set, it will imply that that same element will belong to this right side full set as well. That is how we prove such kind of subset equal to relation when we saw in the set theory lecture. So let's say we have an element B where B belongs to this set. Because if f of something belongs to this set, so B is an element from that set, which is this. Now since B belongs to this set, it means that B equal to FA for some A belonging to A1 intersection A2. So for some A here, I have B equal to FA. Now for some A belonging to this means that A belongs to A1 as well as A belongs to A2 both. So therefore we get B equal to FA for some A belongs to A1 and B equal to FA for some A belongs to A2. So this two, if we combine together as per set theory, it becomes some B which belongs to FA1 intersection FA2. Remember, FA1 is the image of A1, it's a set, and FA2 is a set. So this intersection V2 is just basically this formula, which implies the result. In the same vein, you can prove this in this equality also, where you have to prove an element that belongs to here also belongs to here, and vice versa, that an element belongs to this right hand side set also belongs to left hand side. This is the same, that if your A1 is a subset of A2, then you have to show that if A1 is a subset of, so an element belongs to if A1 should also be an element which belongs to FA2. All of these are simple and goes in same vein, that's why I left it for you. If you just calculate it by your hand, you can easily get the answer. There are two types of functions that we are mostly considerable with. One is called one-to-one or injective function. So this injective function, as the name suggests, it's one-to-one. So it means that f a to b is a function which is called one-to-one if each element of B appears at most once as an image of some element in A. So it means that for an element in B, I could not get two different elements in A pointing to B, or rather mapping to B. Function with versus relation. So function over relation restricts that one element in A cannot map to two different B. That is the restriction driven by the definition of function. However, the additional restriction here we give is that an element of B cannot also get associated from two different elements in A. Formally, we say that for arbitrary subsets AB, f is A to B is one-to-one if and only if let's say there are two elements where if two elements get mapped into same element in B, that is FA1 equal to FA2, eventually will imply that two elements are not different, they are the same. So no two different elements will map into the same set. Formally, if you go by the contrapositive notion of this, you can also see that I can say there exists some element in A which is different. Let's say A1 and A2 are, there exist two elements in A which are different. They must map to two different elements in B. So if there exist A1 and A2 when, if I go for contrapositive, when A1 not equal to A2 imply FA1 not equal to FA2. That is also the same definition, telling it in a contrapositive way. Obviously, you can see that since every element in B can be mapped from one element in A, not more than one, therefore, so for each element in B, I have at least one pre-image in A, and one. So here, A can map to one element in B. So therefore, if a function is 1 to 1 and AB are finite, then we see the number of elements in A must be less than equal to the number of elements in B. Because here, if I have some element association from A, that should be unique association coming from A, or I have some more elements which are not associated also possible. So that's why this set must have more elements than here. Function defines that every element of A should be mapped to some elements in B uniquely. This says that the elements that are present in B must come from an association from only one element in A. So there could be more elements which are not associated from A. So therefore this set is obviously more than equal to than the set of the elements present in A. An example, if fx equal to 2x plus 1, when we are mapping from real number to real number, then we say that this is 1 to 1, because for all x1 and x2, if I see that fx1 equal to fx2, then it automatically implies that x1 equal to x2. So it means that this is 1 to 1. Some other example to prove that it is not 1 to 1. Let's take this example. I saw that there are two elements that remain in this domain R, -1 and 0, which gets mapped into the same elements in the codomain. So for 0 in the codomain of G, I have two different values from which it can be associated, hence making this function as not 1 to 1. So the number of injective functions, again if you think by the rule of product, you can find it easily, because here for m number of elements in A and n number of elements in B, so function definition says each of the first component of this association is unique. So there are m positions. Each of these positions in function, we took any of them. Now here, if for the first A1 we associated with it B1, then for the rest of these from A2 to AM, I cannot use B1 anymore, because that will violate my 1 to 1 principle. So I have n minus 1 choices for the second one, and I have n minus 2 choices for the third one, and so on. I have n minus m plus 1 choices for the last one. So the total count is n into n minus 1 up to n minus m plus 1, which is a popular number because this is a permutation of n elements from n elements. So this is n factorial by n minus m factorial, which is permutation of the cardinality of b comma a, npm. So if you now revisit the previous theorem that we stated and we proved that this is subset equal to, you will see that this will only be equal to if your f is 1 to 1. This proof is also straightforward, and it's just a realization if you realize the 1 to 1. So there are cases when we take a function as not 1 to 1, then this is a strict subset. In the next lecture, we will show that how such an example, why this is a strict subset of the image of the subset that you take. Again, this will be subset equal to this notation. So this is how you define and use 1 to 1 or injective functions. The next category of functions that we study is called onto or subjective functions. Surjective functions are those that let f be a function from A to B, then for all elements here in B, I can have at least one association from it. Note the difference from 1 to 1. Here in 1 to 1 says that there could be some elements in B remains which are not associated from it. But 1-to-1 says that if someone is associated from A, there should be only one associations. However, it says that no elements in B could be left out from A, but it relaxes the earlier criteria that one element could be associated from two different elements. However, no element is left vacant. So for all B, there is at least one A such that I have A to B association. So formally we say that for all B there exists some A such that FA equal to B. So then it classifies for onto functions. Again, since for every B we have some A to associate, therefore the number of elements in A must be greater than or equal to the number of elements in B. So therefore we say that if AB are finite and this function is onto, then we say that this relation is valid. An example, let us take fx equal to xs cube plus 1 when we have a function from R to R, that is real number to real number. Now you can see for each element here in codomain R, I have some element x, let's say y is an element in codomain R which is xs cube plus 1. I have some x which is cube root of y minus 1. And this is a real number. So therefore for every element y, I have some x. And therefore it is an onto function. Similarly, if you see fx equal to x square, and again it is from real to real number, I can find an element in codomain which is minus 4 here, where if I try to see the pre-image, it is either 2i or minus 2i. So therefore I find it that this particular element is not present, 2i or minus 2i is not present in the set of reals. Provided that if we allow set of reals as well as set of complex numbers, then that particular element will be present. But here in our case, since we only allow real numbers, so this is not in the member of this. So we say that this function is not onto, because I have an element whose pre-image is not present. So again, if you might be tempted to think about the number of onto functions possible. However, this counting is not like your product rule, but you may surely try out and see that where it fails. Maybe at the end of the next lecture, we will again come back to this problem when we are more conversant with the function and their properties, because it is non-trivial and we will address it. Now when we declare these two onto and one-to-one functions, so some functions satisfy both this relation. So we call those functions as bijective or one-to-one and onto together. So a mapping or a function is bijective if it satisfies both one-to-one, injective as well as surjective or onto. So it says that for every element here in B, I have an image in A, and for every element here in A maps to a particular unique element in B. There should not be two different elements in A which maps here. So the first formal condition satisfies the onto thing that we just showed here as definition. The second one says that there should not be any element other than A in this set which maps to B where A has already mapped. So for a particular B, there will be one and only one association coming from A. That is the restriction given by bijective mapping. So as you can see that for every B I have only one and only one A, then automatically if AB are finite, this is bijective, it follows that both cardinality should be same. So therefore sometimes to prove whether two sets having same number of elements, we prove that they are bijective. So their mapping, we define a mapping in such a way that that mapping is bijective. Then only we can prove. So in a series of lecture, after we complete this set relation and function, we will see that how such counting of sets can also lead us to such kind of inequalities to prove it. The properties of set will lead us to such kind of inequalities. To sum up everything with respect to one picture, we will say that let's say this is my domain and this is my codomain. So here you see this is one-to-one onto mapping. Each element of B is mapped to some elements from A, and no elements of B is mapped from two different elements in A. So it is one-to-one onto. Here you see it is not onto because there is some element in B here. This one is not associated from any element in A. This is onto but not one-to-one, because every element in B has association from A, but not one-to-one due to the first element, this element in B, because it is associated from two different A's, which prevents it to be one-to-one. Neither one-to-one nor onto. This is nor onto because there exists an element who does not find any association from A. Not onto because this element of B has two associations from different elements in A. So this is neither one-to-one nor onto. This one, as if you see it, it's not a function at all, because the basic limitation of function says that an element of A can be associated to only one element, a unique element in B. So therefore, that's why we define that every relation is a function provided that the tuple has first component as a unique element in it. So this element presents in this tuple as well as in this tuple. So it's a relation, but it could not be a function. With that, if you try to think more, see that now since we have a handle to associate two sets, now let us try to think our algebraic system, which is indeed an abstract system where we define that in a set of integers we added them, we subtracted them. So we define functionalities or operations among those. So we took two integers and have a binary operation among them and try to find one integer. So then there is a formal definition which is called binary operation between two non-empty sets AB. We call it as a function where we took two of them. This function is the operation between two of them which results an element from the set B. If that set B is a subset of A, then we call that binary operation to be closed under A. This, when you see that you add or subtract integers, then you produce an integer. Therefore, your B that you produce remains as a subset of integer. In case of multiplication also this is holds. That therefore the binary operation F, which is addition, multiplication, subtraction, over the set of integers are closed under it. However, if you look at division, two integers may divide and produce a rational number. Let's say you divide 14 by 6. Then 14 by 6 will never produce an integer. Therefore, it is not closed under division, the binary operation called division. So the number of such kind of binary operations possible is the cardinality of set B to the power A square. It is pretty straightforward because number of function is cardinality of B to the power the number of elements in the domain. The number of elements in the domain here is A square as per the cross product. Number of elements in the cross product is concerned. Unary operation, you have used it to make unary minus, that is minus 2, minus 5, such minuses. So it's a particular operation defined over an element of itself to itself. It's called unary or sometimes monary operations on it. Let F be a binary operation defined from A cross A to B, then we call F as commutative if you take two different elements from A and perform that particular operation in this straight order as well as in the swapped order. Then if these two are the same, then you call it as a commutative. Suppose you take addition operation over the set of integers. So x plus y equal to y plus x. So addition is commutative over the set of integers. You take multiplication, AB equal to BA, it's commutative. You take subtraction, A minus B is not equal to B minus A, so subtraction is not commutative. Associativity tells that if F is a closed binary operation and you have three elements, arbitrary for all three elements, if you try to first operate the first two elements and the result you operate with the third is same as if you operate the first element and with the result of second and third. So for example, addition and multiplications are associative. So you multiply first two and with the third one, or you multiply first with the second and third one together, is results the same. Okay, so here are some examples. As we are saying that x minus y is definitely not closed because I have 1 minus 2 equal to minus 1, and you see the closure means that, so this is from z plus to z plus and set z. So x minus y, this x and y are positive numbers, integers. So the output is to set z, that is okay because it could be positive or negative. So this function is a valid function. However, to have closure, I need B to be a subset of A. That means wherever I go, I need this answer to be a subset of Z plus, which is not the case here. That's why this is not a closed binary operation. Unary operation, you can say that from R plus to R plus, the reciprocal of X, 1 by X, is an unary operation. X minus Y, again, from Z cross Z to Z, it's a closed operation because your answer is in the set of integers. Though it's a negative, but it's in set of integers. It's neither commutative nor associative because if you go for commutative, X minus Y is not equal to Y minus X. So it is not. Nor associative because if you try to associate with Z, so X minus Y bracket minus Z, the answer is X minus Y minus Z. Now if you do Y minus Z first and then do X minus of that, it will be X minus Y plus Z. So those two are different, hence it is not associative. Similarly, I leave it to you to find it, but the answer is this is commutative. As you can see, commutative is very easy to see because B plus A minus B into A is same as this. So if I exchange B and A, this is same. Associative, if you compute with C, this rule of association, you will get that this is also associative. So, this is some of the examples that we saw that how we categorize binary operations. There are more properties of binary operations that we can write. So, one is called identity. Identity is basically finding an element which is from set A. Suppose A cross A to B is a binary operation. So, we find an element which we call an identity element. If we see that f A of x, if we operate A with x and we operate x with A, so it is commutative first of all. And if we operate x with A, we will get the result A for every A. So, see, for addition binary operation, 0 is your identity element because x plus 0 equal to 0 plus x equal to x, or rather A plus 0 equal to 0 plus A equal to A. So, 0 as x is your identity. For multiplication, 1 is your identity because A into 1 for any A equal to 1 into A equal to A. So, if f has an identity, then that identity is unique. So, there could not be two elements which is an identity, both are identity elements. This could be easily shown by contradiction. Let us see that we have two elements x1, x2 belongs to A. Now by definition, since if you choose x1 to be your identity, then it will operate on any element and produce that element as answer. So therefore, if x1, x2 will produce x2 as answer. And similarly, if you choose x2 as a identity, then your if x1, x2 will also produce x2 as an answer due to this relation. So therefore, if x1, x2 will produce x1 as an answer, it's a commutative. So if x1, x2 is commutative to if x2, x1, x1 will be the answer if you choose x2 to be the identity, and if you choose x1 to be the identity, the answer will be x2. So this is leading to contradiction because these two identities are not different. So therefore, if if has an identity, then it should be unique. Example, the same example I revisit, a plus b plus 0 minus a plus b minus ab has 0 as the unique identity because a0 is this, which is equal to f0a. Projection operation is, let's say we have two sets AB and we have a subset which is the subset of Cartesian products of A and B, which is a relation basically. So we say the projection of C to A, where we only take whatever be the value of the first component, whatever is the value. So this is C to A means it is from A cross B to, it's a subset of A cross B to A. Now we take only the A values as an answer. Then it's a projection on the first coordinate. And if we take the other one, it is a projection on the second coordinate. Let us see first a property first, then we will give an example and tell you where this projection is needed. Property is that if C is equal to A cross B, then both projections are onto functions. I think you can prove it very easily. So that therefore to have it onto, you have to prove that for every A here, I have some element from where I can map into. Since it is equal, therefore this particular C have all possible pairs of A and B. So therefore, for some element A, I will definitely have an element whose first quadrant is A, and therefore pi A is onto. Similarly for pi B as well. Now an example, let's say I took a parabola in the Euclidean plane where my points are xy and parabola is y equal to x square. And I took the points from the set of reals. I constructed a subset, and the subset is only the points over that parabola. Among the whole space of r cross r two-dimensional Euclidean plane, I construct only a parabola subset of points, that is x square y, this point, or rather x comma x square set of points for all reals. Now my projection would be for the point 3 comma 9 is 3, that is I projected into a x-axis only by drawing a straight perpendicular line to x-axis where it projects, and again drawing a perpendicular line to y-axis where it projects 3 comma 9 is 9. Note that this first projection is obviously the set of R, because I took every point x comma x square in my C. So therefore this is onto and 1-to-1 as well. For every point xy I have x to map. But my y is basically x square. So the second coordinate projection pi bc is only a positive number, which is a subset of real. And therefore this is not onto, because not every point that I get in x square I have a corresponding a cross b or subset of c there. Only the positive side is there. It is not 1-to-1 as well, because a point 2 comma 4 is projected to 4, whereas a point minus 2 comma 4 is also projected to 4. So therefore it could be the case that projection operation can keep the onto function, the onto relation, onto behavior of a function, 1-to-1 behavior of a function. It could destroy also. We have seen by this example both the cases. Now why this projection is important? Because sometimes we need to see, let's say in case of parabola example, we see that what are the span of the parabola in terms of the x-axis. What is the span of some function in terms of its y-axis, or in terms of an arbitrary plane? If I give it to you, project it to that plane. It provides an abstraction with respect to. So what do we do by projection? We are trying to reduce the two-dimensional space into one dimension. It gives you an abstraction, and that particular abstraction is very much required in many fields of operations. You will see, so database engineering, you have such kind of projection as a separate operator there. So you will see later that this projection function or operation or primitive of projection is important in many areas. A function is called as identity function if it as a reply or as an association, it associates with only itself. It maps with only itself. Fx equal to x is an identity function. So whatever value of a you choose from the domain, I will give you back the answer as the same value. This is required. You will see later that why this is required to prove and to derive certain properties of functions. We call two functions as equal when, and we say fg from a to b are said to be equal. We write it as f equal to g. If for every value of a from domain, I get the same answer from the codomain or same association from the codomain. For every a, f a and g are the same. However, it may so that you have declared a function in such a way that f a and g are same, but their domain codomain does not match. You cannot call them equal. So to qualify for two functions to be exactly equal, you need to also have your domain and codomain sets to be same, as well as for every element in the domain should be associated in a similar manner in both functions to the other elements in the codomain set. So please remember that though your function may produce identical values for all AB, for all A's, two functions may produce such, but their domain codomain must also be the same to qualify it for equal. Let us take an example. Let us take a function f and g from real to integer domain. We declare it as fx equal to x if it is just the integer. It is floor x plus 1 if it is a real. I mean, it is not an integer but a real. And another function g as floor x. You can easily assume that what we are doing is, if a function is real, not integer, then we are taking the nearest lowest integer and adding it to 1. That means you are just capping it above. If it is an integer, we are keeping it as it is. So it is just like having a floor written in a different way. So these two functions are equal. If you try to justify for all a, this you will get the same answer for every x belongs to r. So we call these two functions as equal functions. With this basic notions of identity equal functions, let us define an important concept in function which is called as composite function. So till now we have declared only functions to associate with one set with the other. So this function composition also allows us to compose a set two functions together. For example, I could declare functionality from set A to set B, and I could also declare a functionality from G from set B to C. Now you can easily see that there can be some element in A which maps to some element in B, and that same element in B can get mapped to some element in C. Therefore, I could have a transitive mapping from A to C via G. So I can see that I could declare a function called GOF, which is from A to C, by writing it as first I apply F and then I apply G for all A. So this kind of a function is called as a composite function. So it is not the case that your codomain should always be the domain of the next function that you compose on. It is sufficient if the range of the f, that is f of A that you get in B, matches with this domain of G, or rather the range of the f A is a subset of the domain of G. Then only it is qualified, because I only want to transfer this function to a different domain and to associate it with C. So therefore the range must be a subset of this domain. It is sufficient for function composition. For two identity functions, which identity functions, if you again remember, it gives back the same value as as you put as an for association, it just maps back to itself. So therefore IA is a identity function from A to A and IB is an identity function from B to B. Then we say that F operated with IA is equal to F, because IA with small a will give you back to A, which is FA. IB over F, so FA given to IB, so FA will be from A to B, so F is from A to B, therefore FA will be from B. Given to IB will give you back the same FB, so it's the same function you get back. So you compose from the right side, or from first you compose an identity function, then F, or first you compose your function and then give it to identity function, you will have the same. So identity compositions keep the function intact. So an example is from real to real. We say that fx equal to x square and gx equal to x plus 1. So what will be the composition of f o g? So first we apply g and then we apply f. So applying g to x, we get x plus 1, and then applying here fx plus 1 is x plus 1 square. So we get x square plus 2x plus 1. Now we apply GOF, which is basically first apply f, which is x square, and then apply x here. So it will be x square plus 1. So you can see that though I compose it in a different way, it is not always the case that the compositions may be the same. The order of composition, if I change, it may differ. So f of gx here is not equal to g of f of x. Hence, this function compositions are not commutative at all. It does not hold this commutative nature. So for all x belongs to A, there exists some x where I could have that this composition is not interchangeable in order. So it's not commutative. However, the composite function follows an associativity for defining. So if f, g, h are three functions from A to B, B to C and C to D. Now if I first do the function over f and then give it to the composed function h o g, and in a different way we first compose GOF to X and give it to H, both will result the same. Let us first try to understand this. So first of all, equality of the function, as you remember, is for every value of X given to this and for every value of X given to this from domain A should result the same answer. And we have to also prove that the domain and codomain of this function is exactly equal to the domain and codomain set of this function. So let us see that f is from A to B, G is from B to C, H is from C to D. So therefore when we say H composed over G, it will be first you do H, then you do G, so it is from B to D. When you say G composed with F, so it will be first F you do and then compose it with G, so it will be from A to C. Then when you say that HOG composed with F, that means first you do F, then you do HOG, so it will be from A to D. And when you say that H composed with the composed GOF function, so first you do the composed GOF X and then you do the H of that. So therefore it is also from A to D. So these two functions are having same domain A and same codomain D. So one part of the proof is done. Now if you look at this function, it says that it is HOGFX, which is nothing but this whole thing applied to G first, then H, which is with this one, which is nothing but H applied to this over to G, so GOFX, then applied to H, which is this one. And indeed this is just any order of operation of this holds, since the associativity holds. So with the associativity, just we have a trivial definition of composition, which is basically recursive in nature. Suppose I want to have a function association from the same set to the same set. Then we say F1 to be the F, and for all n we say that we compose n plus 1 functions as F composed with n such functions or n such functions composed with F. See, because this is associativity, I am not using commutativity here, because there are n number of X, anywhere you can put the bracket. This means that n plus 1 number of F, I put the brackets over the last n. This means in the compositions of n plus 1 number of F, I put the bracket over the first n. So this, see, the bracketing or the association doesn't matter. That's why this is a recursive definition of n plus 1 number of same function composition. To define the bijective nature of function composition, let us try to deduce certain theorems. If f is a function from domain A to B, g is a function from domain B to C, therefore GOF is a function from, first you apply f, then you apply g, so it is from A to C. If f and g are both 1 to 1, then GOF is also 1 to 1. This is pretty simple, right? If you think the definition of 1 to 1, that what I need to prove? I need to prove that if GOF x1 equal to GOF x2 for two different x1, x2 in A, then x1 should be equal to x2 in order to prove this one. So let us assume for two different A1, A2, GOF A1 equal to GOF A2, which means that G of f of A1 equal to G of f of A2. Now what is G? G is an onto function. So whatever be the G of x1, if it is equal to G of x2, then x1 and x2 will be equal as per the definition of onto function. So f of A1 is equal to f of A2, since G is 1 to 1. Now f of A1 is equal to f of A2, since f is 1 to 1, the similar notion we can propagate and say A1 equal to A2. So hence I got that two different elements from A applied over function f will imply that those two elements are same. It means that two elements from A cannot be mapped to the same elements in GOF. So it's 1 to 1. If f and g are both onto, then GOF is onto. So to prove this, I need to take an element from C, arbitrary element, and need to see its preimage in B and its preimage in A. I need to prove that for every element arbitrarily chosen from C, I got a preimage in A. Straightforward, right? For any z, there exists a y because g is onto. So I get an y where gy equal to z. And there exists an x for that y because f is also onto. So I get fx equal to y. So therefore z equal to gy equal to g of fx, which is composed GOF of x. So for any z which is chosen as arbitrary z, I get an x. Hence, I could say that this range of GOF equal to C, the codomain of GOF. So this function is actually onto, because an arbitrary z if I choose here, I get a pre-image in A. Now a little tricky part, the opposite parts. I give you f A to B and g B to C and their compositions also. And I told you that this composition is 1 to 1. It is interesting to note that if this is the case, then you can prove only one thing to be 1 to 1, that is f, not the other one. Let us see an example. First, let us prove, and then we will see an example why g is not 1 to 1. So assume that f is not 1 to 1. Assume that GOF you are given with an 1 to 1 composition, however your f is not 1 to 1. If your f is not 1 to 1, so there exists an x1 and x2 in A, two different elements in A, which mapped into same element in B, such that fx1 equal to fx2. Now what does GOFX1 then results? GOFX1 results that this will be equal to GOFX2, because if fx1 equal to fx2, then g of that function will also be the same, because it's a function. So the same element should be applied to a function should result the same. So which contradicts that GOF is injective. So therefore two elements, different elements, and assuming that f is not injective is wrong, because we got a contradiction to our given premise. So f is injective. However, g need not be, because let us take an example. F and g is from real to real. Fx is e to the power x and gx is x square. Now GOF is defined as first you apply fx then gx, so e to the power x whole square, which is e to the power 2x. Now see, GOFX is 1 to 1, definitely e to the power 2x is 1 to 1. Fx is 1 to 1, we have proven it. If GOF is 1 to 1, f is 1 to 1 is as per proof. But see, g is not 1 to 1, because x square, I have two, it's from real to real. I have two positive and negative reals can give same x square. So this is an example that though GOF is 1 to 1, only f is 1 to 1, not g. The counterpart, if GOF is onto, then g is onto, but need not be f to be onto. Similar lines we can prove that if GOF is onto, then for any z, I have GOF is onto, for any z here I should get a pre-image such that z becomes GOF of x, so g of fx. Now if this is the case, z equal to g of fx, it implies that z has a pre-image called fx in g. So for every z I have an fx in g. What is fx? Fx is just a pre-image from the set of B. So therefore making g as onto. For an arbitrary image I have an fx element in g. The not part of f, take this example. It is from integer to integer, both functions. Now fx equal to 2x, gx equal to floor x by 2. Here, if you see GOF, so first you apply fx, which is 2x, and then give you the floor, it will be x. Now you see GOFX is onto, because fx equal to x is an identity matrix, and identity matrices are obviously 1 to 1 onto all, bijective. So g of fx is onto. Now you see that, is your fx onto? No, because here you have defined fx equal to 2x. So it only maps the even numbers from your codomain to, associates it to something in the domain. So here, if the number, let's say odd number like 5, so 5 does not have any pre-image here, because the pre-image of this element says x by 2, but 5 by 2 is not in Z. So therefore this is not onto. So all elements in the codomain are not associated from all elements in the domain. However, this is onto, as we already proven, because this is clearly onto, because every element here has a pre-image, like because this is from Z and it has a pre-image in Z. So it's a floor function. So every component has a pre-image. This is onto. So it shows that unlike the forward direction, that if F and G are both 1-to-1 and onto, implies that GOF should be respectively 1-to-1 and onto. The backward direction says if GOF is 1-to-1, then F is 1-to-1, G may not, and if GOF is onto, then G is onto, but F did not. So with this, we can understand that there are certain rules in the function compositions that we may define, and possibly in the next lecture we will also try to see some variety of the rules involving these compositions and extensions from it. So we will continue this in the next lecture. Thank you.